Okay, so section 2 is talking about logarithmic functions and their graphs, just like we talked about exponential functions and their graphs in section 1. So the logarithmic function is related to the exponential function. It has a base as well. And so let's just go to the next page. So the definition of the logarithmic functions with base a are, it says for x greater than 0 and a greater than 0 but not a equal to 1, that y equals a log to the base a, log to the base a of x, if and only if x equals a to the y. And the way we describe the function f of x equals log base a of x, and it's called a logarithmic function with base a. So that's as clear as mud, right? So let's kind of demonstrate that. So here is the is just an evaluation of the logarithm. So the base is 2. That's always the number, small number down here. This is what we're taking the logarithm of, 16, and the answer is 4. And the way you deal with logarithms is you ask the question, to what power do I need to raise 2 to get 16? And the answer is 4. Okay, let's write that out. So it's basically saying 2 raised to what power equals 16. So if we take 2 to the first power, that's 2. 2 to the second power is 4. 2 times 2. 2 to the third power is 8. 2 times 2 times 2. 2 to the fourth power equals 16. There we go. So what power do I need to raise the base 2 to get 16? And the answer is 4. So the logarithm of 16 with base 2 is 4. So if I ask the question, what's log base 2 of 8? The answer would be 3, because 2 to the third power, the unknown thing, is equal to 8. What power do I need to raise 2 to get 8? Now if I said the log base 2 of 12 equals what? So the question is, what power do I need to raise 2 to get 12? Well, what we can say is that x is between 3 and 4, because 2 to the third power is 8, 2 to the fourth power is 16, 12 is between 8 and 16. But it's not like you average the numbers together, so it's not that simple. So it's going to be some 3 point something. The question is, what is that something? So here's another example. So we would say what is the logarithm of 27 to the base 3? What you ask is, what do I need to raise 3 to? What power do I need to raise 3 to get 27? What power do I need to raise 3 to get 27? Well, 3 to the first power equals 3. 3 to the second power equals 3 times 3, which is 9. 3 to the third power is 3 times 3 times 3, which is 27. Bingo. So we say that the log of 27 to the base 3 is 3. Now if I did, what is a log of 27 to base 4 equal to? Well, you're asking, what do I need to raise 4 to get 27? Well, 4 to the second power is 4 times 4, which is 16. And 4 to the third power, which is 4 times 4 times 4, is equal to 64. So, it's going to be somewhere between 2 and 3. So you'd have to, what you need to have is, in the old days, you used to have a table which would tell you to figure this out. Now, nowadays, you can sort of use your calculator. The calculator really only does two bases, which is 10 and E, 2.71828. But a lot of the cases in this book and in the introductions, the logarithms are integers, and so you can do this kind of thing. So if I did, log to the base 5 of 125, I'd say, what number do I need to raise 5 to get 125? Okay, so you think, well, it's not 1 because 5 is not 125, so you try 2 times. 5 times 5 is 25. Obviously, 25 does not equal 125, so you try it again, and you get 125, and so the answer would be 3. Now, if you have a fraction, you can still take the logarithm of that. So what we would do is, if you converted 0.0625 to a fraction, which you can do, so don't remember how you do this. You might have forgotten how to do this. So you take this and you multiply by a large enough number that's a multiple of 10, such that you get rid of all the decimal points. So to get rid of the decimal point, we're going to have to multiply 10, 20, 10, 100, 1,000, 10,000. So multiply by 10,000 and divide by 10,000. So we're multiplying by 1, you're going to get 6,200. I don't think you have to multiply by 10,000. I think you just have to multiply by 1,000. No, you have to multiply by 10,000. So you get 625 divided by 10,000. And then you can simplify that by dividing by common factors. I'll just look for my calculator. So you could divide by 5. You can see that they end in either a 0 or 5. So if you divide both sides by 5, you would get 125. 625 divided by 5 is 125. 10,000 divided by 5 is 2,000. So again, you can divide by 5 again. You get 25 over 400. So 125 divided by 5 is 25. 2,000 divided by 5 is 400. You can still divide by 5, so you get 5. And 400 divided by 5 is 400 is 80, right? And again, you can divide both by 5, so you get 1 over 16. 80 divided by 5. Oops, let's just check that. 80 divided by 5 is 16. So the equivalent fraction here is 1/16, which is a lot simpler than you thought it was. So you get 1/16. And so this is the case, because this number is between 0 and 1, we know that we're going to need to raise this base to a negative number. So if you take 4 to the minus 1 power, that's 1 over 4 to the first power, which is the same as just 1/4. So that's not equal to 1/16. And then if you try 4 to the negative 2 power, that's 1 over 4 to the positive 2 power, which is 4 times 4 is 16. So you get 1/16. Therefore, the log base 4 of 1/16 is negative 2. 4 raised to the negative 2 power is 1/16. Now there are certain properties of logarithms which we'll use, and there actually are some more that beyond this, but we're just going to look at these for right now. Log to any base of 1 is 0, and that's because what, ask the question, what do you need to raise a to, whatever a is, to get 1? Well, any number raised to the 0 power is 1. So it doesn't matter what the base is. The log to the base a, where a is any positive value, is 0, because a to the 0 is 1. Also, if the number that you're taking the logarithm of is the same as the base, the logarithm of that is 1. And that's because any number raised to the first power is just that number itself. So let's just give you an example here. So log to the base 10 of 1 equals 0. Log to the base 1000 of 1 equals 1. And that's because 10 to the 0 power is 1, 1000 to the 0 power is 1. Here, if you say log base 4 of 4, what do I need to raise 4 to get 4? Well, I have to raise it to the first power. So it's 1. Log to the base 10,000 of 10,000 equals 1. So we always have this basically means you always have a y-intercept of 1, no matter what your base is. Because the logarithm and the exponential function are inverse properties of each other, we can say that f of g of x and g of f of x equals x. So the logarithm of logarithm of a to the x to the base a is just x, and a raised to the logarithm of a of x is x. So this is f of g of x equals x, and this is g of f of x equals x. And also, if you have an equality where the logarithms are to the same base, for this to be true, then x has to equal y. So sometimes you can solve logarithmic expressions by using this property of logarithms. And also what this is saying is that logarithms are one-to-one properties, or they have the one-to-one property. So remember, logarithms are one-to-one means that for every value of x there's only one value of y, and for every value of y there's only one value of x. So far, probably the most linear functions and the cubic function are one-to-one, whereas the quadratic function is not. So let's just look at how these functions look. And again, we could do this by just plotting a few points. So let's just do that. So we're going to look at somewhere we have log to the base 2 of x. So we have, if we do 1 and so this is it's actually x on this side, and here we have f of x, which is log to the base 2 of x. So here we're saying evaluate the function of 1, log to the base 2 of 1. If you go back to the properties of logarithms, the log to the base 2 of 1 is 0. If I do x equals 2, log to the base 2 of 2, that's also the property of logarithms. Log to the base, where is it here? Log to the base 2 of 2 is 1, so that's 1. If I did 4, log to the base 2 of 4 is 2. What do I need to raise 2 to do to get 2? I mean, what number do I need to raise 2 to get 4? 2 times 2 is 4, so it's 2. So you can see if I plot that, I've got 0 so at x equals 1, I've got 0. At x equals 2, I've got 1. At x equals 4, I've got 2. And you could also do half. So log to the base 2 of a half is going to be -1. That's because 2 to the -1 power equals 1/2. So you can see if I go to half, I'll go down to, so when x equals 1/2, x equals -1, which is right there. Okay, so you could pick some integers, specific integers that work out so that you get, well, not this is not integer, but certain values of x, so the answers are integers, and then you could plot the points. So that's what the function log base 2 of x, if you did where f of x equals log base 3 of x, this is still 0. Instead of 2, we'd use 3, which would give us 3. Log base 3 of 3 is 1. And here you'd have 9. The log of 9. Base 2 is base 3 is 2. 3 times 3 to the second power is 9. And you can see that. We won't see all the points. This point's the same. If you go to 3, you get to 1. You'd have to go all the way out to 9 to get 2, which is off my scale. Also, 1/3 would be equal to -1. So if I go to 1/3, I'll be down at -1. So again, you can plot those. So those are kind of the parent functions. Parent function for log base 2, parent for log base 3, and you can see that, you know, if the base is smaller than 2, it's going to become more stretched out in this direction. If you have a higher base, 2, 3, 4, it'll be flatter. So that's kind of the general shape. They have an asymptote here at vertical asymptote at x equals 0. So it does not exist at x equals 0. So here's the information. Okay, so here's the information about domain range, x, y intercepts, vertical asymptotes, and horizontal asymptotes. And I'm showing you the logarithm to base 2 of x. So that's this one right here, I think. Yeah, it's the red curve. The blue curve is log base 3 to the x. But all of them have very similar domains and ranges. So domain is the possible x values. So you can see that there are no values of x less than 0, less than or equal to 0. So the domain is from 0 to positive infinity. The range, you can see, goes from negative infinity. This approaches negative infinity as you approach 0. And this also approaches positive infinity. So the range is from negative infinity to positive infinity. They all have the same x-intercept of 1, just like the exponential function had a y-intercept of 1. There is no y-intercept because these curves approach the y-axis, but they never cross the y-axis. There is a vertical asymptote at x equals 0, and there are no horizontal asymptotes. So this flattens out, but it never flattens out to a given value. It'll continue to increase to infinity, increases slowly to infinity, but and you can see the red curve, the blue curve has the same things. It has the same domain, range, x-intercept, so forth, so on. So these are the parent functions for the logarithmic. And you know, we're going to, when we look at how transformations are done, you can plot the parent function by picking maybe 4 points, probably, x equals some fraction, whatever, based upon the base. So it would be 1/2 for a base of 2, 1/3 for a base of 3, 1/4 for a base of 4. You'd pick 1. That always intersects here. And then you'd pick a value of x, which is the base. So, log to the base 2 of 2 is 1. Log to the base 3 of 3 is 1. Log to the base 4 of 4 is 1. And maybe one additional point where you have the y value equal to 2, maybe, something like that. And once you plot the parent function, then you can apply the transformations. Now, this is one thing we said was that the exponential function and the corresponding logarithmic function of the same base are inverses of each other. So if you remember back to chapter 1, the properties, what are the properties of inverse functions? One is that f of g of x equals x and g of f of x equals x, and we demonstrated that earlier. Also, the functions are symmetric about the line y equals x. So that's the green curve here. So you've got the exponential function, the logarithmic function. You can see how they're mirror images of each other. Now the reason these can be inverses of each other is because the exponential function and the logarithmic function, they're both 1-to-1. For each value of x, there's one value of y, and for each value of y, there's one value of x. So here are the transformations. So this is our parent function, and there's a separate parent function for each base. So log to the base 2 of x will be a parent function. Log to the base 3 of x will be a different parent function. Now to have it shifted horizontally, you see that in the argument of the logarithm. So whatever number is grouped with the x against x minus b or x minus h. So if you have x minus 2, b is positive 2, and therefore you would have a horizontal shift in the positive direction. If you have x plus something, then you have x, if you had x plus b, that's the same as x minus negative b. So what you do is you take this value b and you shift it to the left instead. For a vertical shift, instead of the constant being in the argument of the logarithm function, it's outside the logarithm function. So if it's positive, it vertically shifts it at b units. If it's negative, it shifts it down. For a reflection across the x-axis, the negative sign is out front. Negative the log to the base a of x, so that's x reflection. For a y reflection, the negative sign is inside the argument, so that reflects it across the y-axis. Now, one thing is if you have negative x plus 3, not only do you have a negative sign here, but you've also got this horizontal shift. So to get the correct horizontal shift, you factor out the negative sign for both of them. So if I factor out a negative from this term, it just becomes positive. And if I factor a negative out of here, it's positive becomes negative. So you can see if I multiply this out, negative times x, negative 1 times x is negative x, negative 1 times negative 3 is positive 3. So you may be tempted to say this is it's a shift x minus h. You'd have negative 3 horizontal shift, but really it's negative the quantity x minus h. So minus h. So this is going to be, in reality, it's going to be a positive shift in the x direction. You've got stretches, vertical stretch by having b. If b is between 0 and 1, it's vertically shrunk basically, and if b is greater than 1, then it vertically stretches, and likewise if this constant is inside the argument, it's the opposite. So if the constant is inside here, it stretches if b is between 0 and 1, and it shrinks if b is between 1 and infinity. So the same logic applies for all these transformations once you get the parent function. So here's an example of the parent function, y equals log to the base 2 of x. And then here we have the negative sign outside the argument, outside the function, so that's going to be a x-axis reflection. So the original function flips over the x-axis. So these come down, these go up. At x equals 1, doesn't matter. You're going to have the intersection of 1. And so that's an example of the x-axis reflection due to the negative sign. Now, here is the case of where you have a horizontal shift. So this, again, is my base, my parent function, the red curve. And what happens is you have this horizontal shift. So you have x minus h. Therefore, h in this case equals 2, x minus h. So that means it's going to be shifted in the positive x direction. So everything gets shifted. The vertical asymptote gets shifted. So instead of the y-axis being the vertical asymptote, the line x equals 2 shifted. This goes from 1 to 3. Everything just gets moved over and copied. So that is the transformation, is just a shift of everything, including the horizontal vertical asymptotes. And you can see the domain, instead of going from 0 to infinity, is now going from 2 to infinity. So this doesn't change because it's infinity, but this moves to 2. So there are no values of x that can be evaluated at negative values, or at values of x less than or equal to 2. So it's kind of, back in the days of square roots, if we had the square root of a negative number, we could deal with that using complex numbers, but you can never take the logarithm of a negative number. And here shows how the transformation occurs with a y-axis reflection. So the red curve is the parent function, y equals log to the base 2 of x. And if you put the negative inside, what that does is it shifts, it flips everything from the right-hand side of the x-axis to the left-hand side of the x-axis. You're like, I thought you just said you can't have a natural log of a negative number. That's true, because if I put negative 1 in, I'll negative and negative 1, which becomes then a positive argument. So it does make sense. And here is an example of stretching. So if I take my parent function and I multiply it by a constant that is greater than 1, and it stretches it in the vertical direction. If I multiplied it by something like 1/3, it would shrink it in the vertical direction. Whereas the other case is if you multiply by the x by a number, what that does is it's going to, instead of stretching it in the vertical direction, it's going to shrink it in the horizontal direction, which in this case is kind of the only case where it does the same thing, is that when this is greater than 1, it's shrinking it, but it's essentially stretching it in the vertical direction. So if I take this and I shrink it in that direction, it's the same as if I took this and I stretched it in the y direction. And there's a special case where we have the logarithm where the base is e, and the main thing is we just give it a special name, which we, instead of doing log to the base e, we just say ln, which stands for the natural logarithm. So when you see the natural log, it's automatically base e. On your calculator, this is one of the two options that typically is available. You'll have log to the base 10 of x, or you'll have ln of x. These are the two calculator options. Now, if you have a base other than 10 or e, you can still do it, but you have to use some properties of logarithms where you can change the base, which I think we get to in this class. If not, you'll get to it in calculus. So the natural log and e to the x, these are inverse functions because they have the same base. This is the same as log to the base e of x. Okay, so I'm going to stop that and we'll continue on in a separate video.